Simon Beer, once again, and I'm chairing this session. And our first speaker is Alex Gagliano, local here, is in his final year PhD, hint, hint, here at University of Urbana-Champaign, and he does not only know all the local things that you may be curious about, but he also knows a lot about elastic that he's going to talk about. Please take it away.
Thank you so much, Simon. Right, so I'm Alex Gagliano, and in just a little bit we have lunch, which will mean that we're halfway through Boom, 2.5 days from the start of the explosion. And I think in the past 2 days, to me at least, two kind of prominent themes have emerged across all of the talks. One is that right now, for a lot of the models that we're using across multiple different time domain analyses, accurate, realistic simulations are absolutely critical for augmenting our data sets, especially before LSST comes online. So that's one. And number two is that photometric classification is not going away. We need to find better ways to do it. It's hard, especially with the cadences proposed by LSST, but it seems like we're starting to find better ways to do it, and I support these efforts wholeheartedly. And I think those two prominent points are also the perfect foundation for me to build off of and discuss our simulational framework for a photometric data set building up into LSST called the Extended LSST Astronomical Time Series Classification Challenge, or ELASTIC. Apologies, there are some contrived acronyms in this talk. I am responsible for some of them, but to be fair, some of you are too. So, okay, so everyone has their favorite version of this, this movie, and this is mine. This is showing the number of supernovae that we've discovered that we've been able to follow up spectroscopically or not since the year 1800. On the left, I'm showing a sky map of these discoveries, and on the right, I'm showing a probability density function as a function of redshift. And you could see, unsurprisingly, early on, we do fairly well with the number of spectra that we're able to obtain. And in just the past couple of years, we find that now we're completely swamped in data. We don't have enough spectra to follow up everything we want to look at. Unsurprisingly, the things that we don't have spectra for push out to higher redshifts. And so photometric classification is now this big open question that's really going to become a big issue with LSST. And the question is, if we want to develop machine learning methods for photometric classification, where do we look? We have this big parameter space of potential methods that we could co-opt potentially from computer science, and how do we go about exploring that parameter space? Well, there are some Bayesian people in the audience, so if you would go about sampling the space, potentially what you might want to do is initialize a set of walkers, each at slightly different starting positions, and each task them with solving the same problem. And they'll do it maybe a little bit differently, but if they all converge on a similar solution, this tells you that the solution is probably pretty robust. And this was actually done in late 2018, early 2019. The walkers were people, and the challenge was called plastic. So the Photometric LSST Astronomical Time Series Classification Challenge was launched on Kaggle, and the participants were tasked with finding novel ways to photometrically classify simulated LSST-like events in this big training and testing framework. And so for the data set, 3 million full-phase light curves were provided in UGRIZY for a series of both galactic and extragalactic transients for which we have models. And this has really now become like the gold standard data set for training and testing machine learning classification tools. So I've thrown up just a couple of papers there. Gotham's also really excited that there's a paper that uses the data set that is not in astronomy, in like cardiovascular disease or something like that, which is very cool to see. So plastic, by and large, was an overwhelming success. However, there were some limitations that were known at the time, and in general, the data that was presented is not the way that we're going to do science with LSST. The way that we're going to do science with LSST, as you've heard a lot of times over the past couple of days, is in a framework similar to what you see up here. This is a screen grab from Yeezy Peasy, which was developed by Dave Coulter and Dave Jones, who's there in the audience. And if you see a lot of transients and you're not sure what to follow up in detail, you might look at the most salient features that you've collected from that transient, like an incomplete light curve, some data points. You might look at the postage stamp of the field to see if it's actually real, if it's associated with a big host galaxy. You might have an estimate of the photometric redshift by some neural networky method with uncertainties that you might not know or that you might know to be huge. And based on all of that information, you want to make a decision about whether you want to follow up this thing or not. And so to extend our simulations from plastic to build us out to better prepare for LSST, we are making some modifications into and baking them into Elastic. So the three that I want to highlight here, number one, we now realistically associate transients with their host galaxies using a data-driven methodology that I'm going to be talking about a little bit later. That was the part that I primarily contributed to. Number two, we now simulate redshifts probabilistically and provide posterior distributions as opposed to point estimates of the redshifts with realistic uncertainties as you might expect from LSST. And number three, we now stream the data in Avro format as you might expect from actual LSST AP, as opposed to providing the full phase light curves in the hopes that broker teams will get better at real-time classification instead of just being provided the full light curves, which is a little less realistic. So we're evaluating brokers' abilities on this stream data set. What we're testing is a little bit unclear. It's an iterative process between our simulation team and the broker teams to figure out what's realistic to expect of the brokers and what's realistic to provide within the streaming data to begin with. So we've been in constant communication, and the role of the broker is a little bit fluid, but we, at minimum, want the brokers to be able to provide some scientific insight into the alerts that they're provided, some basic classification results. There are some potential additional roles where they might play a hand, but with time we'll see how true that actually is. And then the alert stream, as I mentioned, we want to have more realistic environmental correlations and a representative sample of events as we might expect to see with LSST. Obviously that's a big caveat because we don't know completely what we'll see with LSST, but to the best of our ability at this time. So we've updated some models from the simulational framework that we set forth in plastic. Namely, there are multiple galactic models that are new that have been integrated with a couple of people, specifically Konstantin Melanchev, who you heard from earlier this week, and Shifang gave a dwarf nova model that we've contributed to. Sorry, Shinan. And we've updated multiple models in the simulation framework as well. So there are multiple stripped envelope supernova models that we've contributed, and M-dwarf flares, kilinovae. There's been lots of simulational work in kilinovae over the past couple of years, unsurprisingly, and we've integrated those to the best of our ability into this framework. And the images I'm showing here, bottom left, are the stripped envelope supernova photometric templates, which have been, we're very grateful that they've been provided by Fed and a couple other people. And then on the right, you see a distribution of simulated galactic transients on the top, and then on the bottom, localization maps of kilinovae simulated by Deep Chatterjee, who is also attending remotely. So at its core, the simulation that we're building on top of is SNANA, which is a code developed by Rick Kessler, who's on the Zoom, I believe. And SNANA is a forward model which starts from a rest frame SED from a series of different transients and then propagates through all of the observational effects that we think we're going to have happen and simulates different LSST passbands for individual observations. And the piece that we've been working really hard on integrating is this earlier chunk right here to realistically associate transients with their host galaxies and to have that association informed both by observations using a catalog called GHOST that I consolidated last year, and a simulation called CosmoDC2. And this is a synthetic sky catalog that pushes all the way out to redshift of 3. And so we want to convolve the information that we get both from observed samples of low redshift supernovae and their host galaxies with simulated higher redshift galaxies such that we haven't been able to observe to date. And we do this using an approximate nearest neighbors matching algorithm. The matching algorithm is called ANOI. I don't have time to get into it, but ask me later how it works, because I'm really interested in it. It's actually used currently by Spotify to come up with song recommendations after the one you're listening to. And the advantage of ANOI is that it's not a perfect nearest neighbors matching algorithm, but it's very fast. So we can take galaxies that are in GHOST, we can find their similar counterparts in Cosmo DC2, and we can scale up the data set of likely host galaxies for each transient to about 12 million galaxies in about 10 minutes. And as an intermediate data product, I just want to pitch, it's probably no surprise that this is the piece that I worked on, given the slide, but I want to pitch that this paper is now out on arXiv. SCOTCH is the synthetic catalog of optical transients and correlated hosts. We're really excited about it, and it's one piece in the pipeline of simulating the full elastic alert set. So feel free to check it out at the arXiv link and let me know if you have any questions about it. And all the data is on Zenodo as well from it. Okay, so we've done all this work. We've encoded all of these host galaxy correlations into the pipeline, but of course, the observations that we get don't correspond directly to the underlying ground truth of what transients happened in what galaxies, right? So we see a transient, and we have to do some matching to figure out what galaxy we think it came from. And traditionally, this is done using DDLR, where the distances between the transient and lots of galaxies in the field are normalized by the radius of the galaxies in the direction of the transient. So the hope is that when you do this, you put big and small galaxies on kind of equal footing in making an association more accurately for a given transient. This is not a perfect method, and in the simulational framework, that's a good thing, because we use DDLR after everything to come up with a list of 2 most likely hosts ordered by DDLR that we put into the alerts for brokers to see. Now, again, this is not ground truth, so some events could have 0 associated host galaxies by this method if they're at high DDLR, because we impose a manual cut. And it's possible that the most likely host galaxy by DDLR is not the ground truth that we simulated. So we hope that brokers can develop algorithms that are robust to this kind of thing, because it's what we're going to see when LSST comes online. And then a piece that I did not work on that is very impressive is a piece done by Alex Maltz, who you heard from yesterday, in the generation of probabilistic photometric redshifts. So Alex Maltz used a machine learning method called normalizing flows to be able to do this. Normalizing flows allow you to learn a probability density function in this big multidimensional parameter space efficiently and flexibly. So you can think of it a little bit like kernel density estimation, except it's more flexible to some really complex distributions. And in normalizing flows, what you do is, if you have this distribution that you don't understand very well, you can't model, instead of trying to model it directly, you take a very simple multidimensional PDF, like a multidimensional Gaussian, as you see on the left, and then you learn a function that transforms the simple distribution into the complex distribution, and it's invertible, so you can go back again. This is called the bijective function G here. And the nice thing is that once you've learned that function, you can sample from this simple distribution on the left, apply the function to transform it into the complex distribution, and all of a sudden, you've learned your multidimensional PDF on the right here. And so we use normalizing flows to model the host properties and how they're all correlated with each other, and then to draw a posterior distribution of realistic photometric redshifts for each of the simulated galaxies in our sample. And we provide both point estimates and full PDFs in the alerts. We're hoping that people will eventually start moving toward the full posteriors and working with them as opposed to the point estimates, but progress moves slowly. So in terms of what's in the alerts, here's just a little screen grab of a couple of pieces of it. The mini batch of alerts was already sent out to get brokers to just start playing with Avro files, make sure they can ingest them just fine. We also have a training set and a test set. The training set, is being sent out and streaming now. The test set will be sent out starting in around September, and it'll be 3 years of LSST compressed across 3 months. So the MJD dates, I think, will correspond to the 3 years, so we'll all just pretend that 3 months starting September will feel like 3 years, which might be the case since I'm applying to postdocs. Okay, and this is a classification challenge, so that's going to be the main metric by which we evaluate broker performance. There are 7 brokers that will be fed the full stream of LSST data. I couldn't find a Pitt Google logo, so that's not the logo, but that's just a picture of Michael Woodvasey. But there's a hierarchical schema that's been developed by Gautam and Alex Maltz to evaluate the classifications of the brokers. And it's a hierarchical schema, as you might expect from real data, because sometimes we can only say if it's a periodic or a non-periodic source. Sometimes we can say what subtype of type 2 core collapse explosion it is. And so providing this kind of flexibility for the brokers, I think, allows for some model diversity and increasing confidence with additional alerts as they come in. And I just want to give another shout out to Alex Maltz's talk yesterday. It is not necessarily the best way to meet our science goals to evaluate the brokers based on classification. So it's a classification challenge. I have probably said that many times at this point, but we should be working to evaluate brokers on many other metrics across many other axes to make sure that they'll be survey ready for all the things we want to do with them on day 1. Okay, so there are a couple of limitations of Elastic that we're well aware of. We weren't able to simulate postage stamps because that's very dependent upon local host galaxy correlations that we weren't able to simulate at this stage in the pipeline. Because we're not simulating postage stamps, the photometry that we simulated is completely disconnected from the DIA efforts to generate light curves. And so all of the different contaminants that people think about in DIA, we are thinking about but not actually doing. And so the extent to which the contamination will affect our classification is really unclear to date. So I'll just conclude by saying Elastic is right now the state of the art in massive transient simulations. We're really excited about it. There are the 3 main points that we've contributed to the models from Plastic, and the data is streaming now. We want to figure out how to do pixel modeling. It's maybe the next step in the pipeline, but we're excited to hear what questions you may have. And I'll stop there and say thanks for your attention.
Thank you very much, Alex. Any questions in the room or on Zoom? I see several. I start from this side this time. Introduce yourself for those people on Zoom.
Hi, Sebastian Gomez. Great talk, very interesting. So you've gone ahead and gone through the process of associating transients with galaxies in a simulation, but I care about the reverse, right? Given a transient, which one's is most likely galaxy. So if computational computational time is not an issue, what method would you recommend is the most robust between the ones that you mentioned for associating?
Ooh, for associating transients
Yes.
with hosts. That's a great question.
Because there's a DLR that's just simple probability of chance coincidence. Closest one is obviously not
Yeah,
robust, but
it's biased, but I can plug Ghost,
Yeah.
which is based on a set of methods. There's a modified DLR method in that, and it's triage. So if the DLR method fails, then it moves on to an additional method based on image pixels.
okay.
So the thinking is that for like low redshift galaxies, for example, that in pan-stars are pretty fragmented at the catalog level, you'd still be able to recover the center of the true host galaxy directly from the image.
Okay, so it uses like a ratio of like flux at the supernova location versus
Yeah, it traces the image gradients to the location of a local brightness maximum, starting at the location of the transient. So the thinking is that if you have the light profile that you're embedded in of the host galaxy, you can then just follow that to the center.
Great. Any other questions? I see 2 on this side. I'll go here, here, and here. Please keep it short. Yeah.
Thanks. Great talk. sorry if I missed this. I was just going to ask quickly if there's something like distance from the host center for, when you think about AGN or TDEs, et cetera.
Yes, very good question. There is distance from the center, and actually the offset of the transients were simulated using like the Sursic profiles of the galaxies and doing something like, you'd expect more transients where there's more starlight. Of course, for different classes of transients, you would expect different radial distributions. We have not encoded that information in the simulations yet. But I'm really interested in it, and I hope we do.
Hi, thanks for your talk. My name is Samaya Kakbash, and I wanted to ask a question about the stripped envelope supernovae that you mentioned. My assumption was that they've been simulated based on Vincenzi's model, but then I saw like our templates also there that you mentioned. It's been updated based on that too. So I was just wondering how exactly it's been updated. Has it been like implemented in the current release data? I was wondering.
Yeah, that's a great question. So if I'm not mistaken, both the updated Vincenzi models that take into consideration host galaxy extinction and y'all's like photometric models have both been integrated into the latest iteration of the elastic simulations.
Before we move to the last two questions, can you stop sharing such that the next
Sure.
speaker can set up presenting through Zoom?
Hi, Alex. It's Patrick. Really lovely talk. I did have a question. So if I had my own classification algorithm or recommendation algorithm and I wanted to connect up with the Elastic and broker teams to get access to this data and start testing it in time to, test my algorithm, how would I go about doing so?
Great question. So I mentioned that the data is split between training and test. The training data set is both sent out as Avro alerts and also exists in FITS files. So if you wanted, you could process the FITS files directly, because if you're not a broker, it's a little hard to work with the Avro data yourself. So that's one way to do it if you're just looking at like an independent classifier and you're not connected to any of the big broker teams. The other thing that I would say is that, and maybe this is a plug for Gautam, but I think Antares is pretty easy to add filters in if you want your own customized classifier to be able to see how it works on that. And that allows you to work with the interface of a broker with minimal overhead of actually being part of the team.
Yeah. And the very last question from Zoom, Martin.
I think Rob has something he wants to add.
Hook into the Elastic Comms channel on the LSST Slack. That's where you can get all questions like that answered easily.
Great. And so very last question from Martin on Zoom. Please go ahead.
Okay, thank you. So this is really great. You have a galactic transients, but this is like an extra galactic field, right? So RA and DEC doesn't care about the star density and so on. Are there plans to either make like a more full sky simulation or a simulation in the galactic disk? This is question one. Question two is about the timestamps. Do you use some specific opsims to put the timestamps in the light curves, or is like a combination of opsims?
Yes, okay, both great questions. Let's see, for the first one, are there plans to simulate a more full sky simulation for the galactic transients? That's what you're asking?
Yeah, right. Or a specific field in the galactic plane.
At the moment, there's nothing that I'm aware of, but we've released all of our code and all of our models and all of our data, so I think it should be not too difficult if you want to just change like the footprint, for example, that you want to look at in the sky for a specific... Oh yeah? So Gautam suggests that I'm wrong and that maybe there is a different sky footprint being simulated. He can probably answer in more detail in the chat. And then the second question, let's see, could you remind me?
Yes, about the postage stamps. Is this like a given opsims realization where you put all the timestamps?
Right.
For the light curve?
It is a given realization of opsims. I'm not sure which one. Baseline 2.0.
Okay, thank you.
Yep.
Let's thank Alex again. Great talk. And our last talk this morning, local time.